giving you a little bit of a change of pace from the rest of the, excuse me, the rest of the workshop. I'm going to talk about computational thermodynamics with free energies computed from first principles. Let's see, you can see my mouse, I hope. So I'm going to talk about, I'm going to introduce solid solutions and also high entropy alloys. Then I'm going to explain how to read phase diagrams. Those are alloy phase diagrams as functions of composition and temperature. Then I'm going to make a little detour into a discussion of something called the Bain path. The Bain path is a sequence of distortions of cubic structures that take you from a body-centered cubic structure through a tetragonal intermediate to a face-centered cubic structure. I'll show that first in the context of iron, and then in the context of a certain binary alloy that I'm going to discuss in detail further. Then I will remind people about basic thermodynamics. I'll tell you about energy, also known as enthalpy, when the energy is taken at constant pressure, the entropy and the combination of the two that makes the free energy. And I'll discuss the different sources of entropy. Configurational entropy having to do with the swapping of chemical species, vibrational entropy, and electronic entropy. And I will do this in the context of two different examples. Most of the talk will focus on the indium-tin binary alloy phase diagram. I'm going to focus on that because that's what I've been focusing on in my own work for the past several weeks. And then I will also tell you about some recent work in a high entropy alloy of molybdenum, niobium, tantalum, and tungsten. And people can just chime in with questions as they wish as I go, and I'll also pause every now and then to see if there are questions. Okay, so first, let's think about solid solutions. So solid solutions are random mixtures of different elements, and these mixtures form single phases that are stabilized by the entropy of the substitution of one element for another. So these solid solutions occur most readily when we have combinations of elements that are chemically similar so that they can substitute for another, such as, for example, the combination of indium and tin. Indium and tin sit right next to each other in the periodic table, and they share many chemical properties with each other. On the other hand, because they are adjacent in nearby columns, they are not fully equivalent. In particular, tin, with chemical symbol Sn, tin has one more valence electron than indium, and that will play an important role in the discussion. I'll also talk about high entropy alloys. High entropy alloys are just solid solutions that have fairly large numbers of chemical constituents. For example, MONBTAW has 4 species, and chromium, manganese, iron, cobalt, nickel has 5. These are some of the popular examples of high entropy alloys. Okay, now let's remind ourselves how to read a phase diagram. So I'd like to get my phase diagrams from the Association of the American Society of Metals, ASM. And this is their phase diagram of indium tin. It has many phases. At high temperature, which is on the vertical axis, you see the liquid phase. The horizontal axis takes us from pure indium on the left to pure tin on the right. And at moderate temperatures, such as, say, room temperature, which is right down here at the bottom of these colored regions, it takes us through a sequence of 4 solid phases. One of the phases is labeled indium, but it's indium in parentheses because it's not pure indium. It's actually a solution of indium with up to about 10% of tin dissolved in the indium. Then next over is the phase labeled as indium 0.75, tin 0.25, also called indium 310. Even though they give you the composition to 2 significant figures, notice that it is also a solid solution with a wide composition range. Then there is a coexistence region. I'll talk about that more in a moment. Before we reach the next solid phase, indium 0.2, tin 0.8. That's also a solid solution with a wide composition range. And then finally, tin in parentheses, again in parentheses because it has a sizable amount, it can have a sizable amount of indium dissolved in it. And notice that it says RT, that RT is because that's the stable phase of tin at room temperature. But you also see down here in the lower right-hand corner, tin LT, that's the low temperature phase of tin. There are 2 different phases of elemental tin, one at low temperature and then one up here at higher temperature. So all of these solid phases are separated by coexistence regions. And let's take a look at this biggest one. So this biggest one includes, for example, a 50-50 mixture of indium and tin. If you have a 50-50 mixture of indium and tin at temperatures below 120 centigrade, then that mixture will spontaneously separate into an indium-rich phase and a tin-rich phase. And that's true of all of the coexistence regions. So for instance, here at about 12% tin, you will have phase separation into a solution of a little bit of tin in indium and a solution of a little bit more tin in indium. Now, there are some issues with this phase diagram. Here, by the way, I label the different phases and I also tell you a bit about them. So alpha indium has so-called Pearson type Ti2. T stands for tetragonal. I stands for body-centered because in German, the I means inner, I think is why they call it that. 2 means 2 atoms per tetragonal cell. And the space group is I4MMM. I for body-centered, 4 because it has a 4-fold axis of rotational symmetry. That's how we know it's tetragonal. Okay, so what are some of the problems with the phase diagram? Well, the first problem is that alpha indium and beta indium 310, they both have the same Pearson type, Ti2. So they're both body-centered tetragonal with space group I4MMM. So it looks on the surface of it as if they're both the same structure. And if they're both the same structure, then why are they different phases? So for example, if we go into the coexistence region, why would it separate into a region with less tin and a region with more tin, even though both of these regions share the same structure? Okay, so that's one puzzle that I want to address. The next puzzle that I want to tell you about has to do with these broad composition ranges. So notice, for example, indium. So indium can dissolve up to about 12% tin. And it looks like the width of that composition range appears to be independent of temperature. Well, if we had a solid solution persist all the way down to 0 temperature, that would mean that it's possible to make random substitutions of one species for the other species. And that would then create an entropy that would violate the third law. So remember, the third law says that the entropy should vanish in the limit as temperature vanishes. Um, but these broad composition ranges, alpha and gamma in particular, seem to be going to low temperature. They seem to persist to very low temperatures. Um, so that would violate the third law. On the other hand, this phase diagram stops at 0 degrees centigrade. But what's relevant for thermodynamics is not the temperature in centigrade, but the temperature in Kelvin. And so the question then is, what would the phase diagram look down here around 0 Kelvin instead of up here at 0 centigrade? And we'll try to figure out how to answer that question. In order to discuss the difference between these two Ti2 tetragonal phases, I'd like to talk about the Bain path. So the Bain path is what you get if you start with a cubic structure and carry out tetragonal distortions. So you could start, say, with a body-centered cubic structure, and you could squish it so that the C/A ratio was less than 1. So it would be short and fat. And that would destroy the cubic symmetry, but leave the fourfold axis. So it would be tetragonal. In particular, it would be what we call a Ti2 structure. 2, because there are 2 atoms per tetragonal unit cell. Here we see Ci2, body-centered cubic is Ci2, C for cubic, 2 for 2 atoms per unit cell. If we stretch the body-centered cubic, we would get a tetragonal structure with C/A greater than 1. Here I've shown the special case of square root of 2. And when you stretch from body-centered all the way up to square root of 2, suddenly the structure becomes FCC. Here is a picture of the face-centered cubic conventional unit cell. Its Pearson symbol is CF4, C for cubic, F for face-centered, and 4 for 4 atoms per cubic unit cell. How do we see that this is face-centered? I think it's quite obvious that this structure on the left is body-centered. The face centering is maybe a bit harder to see. So here I have used Vesta to draw a plane along one of the faces. And you see that there's an atom sitting at the center of one of the cubic faces. In fact, every cubic face has an atom at the center, like this one at the top, this one in front, and so on. But I claim now that this tetragonally stretched body-centered cubic structure actually is face-centered cubic, provided that we stretch by the square root of 2. And here is a figure to illustrate that. So I've taken a 2x2 supercell of my stretched tetragonal, body-centered tetragonal structure. So here we see the 4 unit cells of the 2x2 supercell. And now I've drawn a lattice plane running through the body center. So this is what's called a 1-1-0 lattice plane. And notice that there is an atom sitting, the body centering atom sits at the center of this 1-1-0 lattice plane. And because we stretched by exactly the square root of 2, actually the pink lattice plane that's drawn here is a perfect square. And this atom sits at the center of a perfect square. And so we see that the structure is indeed FCC, but it's been rotated by 45 degrees. Okay, I'll just pause for a moment to ask if there are any questions about that crystallography or the phase diagram. Okay, if not, let's talk about the Bain path, which is the sequence of tetragonal distortions. So here I've plotted total energy in units of electron volts per atom as a function of the C over A ratio. When C over A is 1, the structure is body-centered cubic. When C over A is the square root of 2, which is 1.41, the structure is face-centered cubic. So these are the results of total energy calculations carried out using VASP. VASP is a very popular density functional theory program. It uses a plane wave basis. It's computationally very efficient. The calculations I'm showing you here are done using a variant of pseudo potentials. I mentioned already in a plane wave basis. VASP is highly used program for basic density functional theory calculations. It even has enhancements like random phase approximation and dynamical mean field theory, I believe, is coming soon. Because it's so efficient, it's very popular and actually accounts for it's the most heavily used program on supercomputers worldwide, I believe, and accounts for 20% of all computations done at typical supercomputer centers. Okay, so these are the VASP total energies. For iron, you see that magnetic iron prefers to be body-centered cubic. Or another way of looking at that is that if non-magnetic body-centered cubic iron is unfavorable and iron wants to magnetize, as we all know. If you stretch through the tetragonal region, the energy goes up. That shows you that the magnetic iron wants to revert back to body-centered cubic. And then at this very special point, FCC, you see that the magnetic and non-magnetic have essentially the same energy. So this is what's known as the Bain path. This Bain path is also related to what's known as the austenite-martensite transformation of steel. Okay, here's a graph of the same thing for the Bain path of indium. You see that indium, although indium likes to be body-centered tetragonal, it does not want to be body-centered cubic. The tetragonal distortion is spontaneous. And then you see that there are two minima. One minimum with a distortion of about 1.35, a C over A ratio of 1.35, which is less than the square root of 2. Let's call this beta structure the low C over A ratio. And then we go through the square root of 2, where the structure is temporarily FCC. And then we continue with further tetragonal distortion. Now the C over A ratio is about 1.5. That's greater than the square root of 2. The structure is Ti2 again, but now it has a high C over A ratio of about 1.5. So C over A less than root 2, I will call a low ratio, and I will sometimes call the structure beta. And with a high C over A ratio, I'm going to call the structure alpha. Notice that they are, in a certain sense, the same structure. They are Pearson type Ti2 with space group I4MMM, but they differ in their C over A ratios. And you see that there's actually an energy barrier separating the two. And there's also an energy difference between the two, because notice that the best energy of alpha is slightly less than the best energy of beta. Okay, now remember that beta was the state of indium-3 tin, whereas alpha was the state of indium with up to, say, 10 or 12% tin. And you remember also that tin is one step to the right in the periodic table relative of indium. So when you substitute tin for indium, you are increasing the valence electron count. And so here I show total energy calculations along the Bain path. Instead of starting at C over A of 1, I'm starting at 1.2. And in black, we see the result I showed you previously for pure indium, and you see that that there is a minimum below the square root of 2, a local maximum at the square root of 2, and then a second and somewhat lower minimum beyond the square root of 2. So that's if you have the valence electron count of pure indium. But now we can start increasing the number of electrons. So in the VASP code, you can simply specify that the pseudo potential is the pseudo potential for indium, but the valence electron count is whatever we choose to make it. And so I chose then in red to add the equivalent of 5% tin, in green the equivalent of 10% tin, all the way up to in brown, which I've labeled as beta indium-3 tin. I've labeled that has the valence electron count equivalent to 25% tin. And you notice for low valence electron count, the alpha state, that is the high C over A ratio, is favored, whereas at high valence electron count, the beta state with low C over A ratio is energetically favored. Okay, so that presumably explains the gap that I showed you. It explains why there's this miscibility gap, because think of the states that would be in here as corresponding to the jump from high C over A ratio to low C over A ratio. Okay. So now I'd also like to speculate a little bit about what the physical origin of that behavior is. Why are there these two different states at two different valence electron counts? And so to try and understand that, I've calculated what's called the difference charge density, delta rho, which is the self-consistent charge density minus the charge density of isolated atoms. When we carry out these calculations, we start off assuming that the charge density is nothing but the superposition of independent atomic charges. And then we carry out the self-consistent electronic structure calculation to solve the Kohn-Sham equations. And that solution of the Kohn-Sham equations then gives us the self-consistent electron density that differs from the superposition of atoms. And so within Vesta, we can take the difference between those two charge densities. And here, if we take the valence electron count of pure indium, but we take the C over A ratio of beta indium-3 tin, then this is what the charge densities look like. I'm showing them to you here in a 2x2 supercell. And the red is where charge density has accumulated. And I also show isosurfaces. These little blobs are isosurfaces of charge density that show you where the maximal charge density is located. Okay, so this is an energetically unfavorable state because the charge density is too low to be favored by the C/A ratio. If we now go to the C/A ratio of alpha indium, which is a ratio greater than the square root of 2, then what you see is now the charge density is concentrated in the horizontal plane. The charge density sits in the region of space between one atom and the next atom. So let me remind you over here. Here is a body centering atom, the next body centering atom. Well, hidden back here is a body centering atom and the next body centering atom. And you see there's an accumulation of charge density in the region of space in between, which tells us that a strong covalent bond has formed in the horizontal direction. That strong attraction in the horizontal direction will tend to reduce the A axis. Holding the volume roughly constant will then increase the C axis. And that's what favors this tetragonal distortion, favors C/A greater than the square root of 2. What about the other case? Well, let's now take a small C/A. So this is a C/A typical of the beta structure. Take this small C/A. But now we have the valence electron count of 25% tin. And notice where the charge is located. So let's look, say, at this bond stretching from the upper right-hand corner of the cell down to the body center. This blob of charge density sits exactly along that bond. So it tells us that there are covalent bonds connecting the body center to the atoms in the plane above. Those covalent bonds will try to reduce the C axis and keep the C/A ratio low. Okay, so I think that these different patterns of covalent bond formation then are probably the origin for the relative energies that we saw in these figures. Okay, so I'm about to launch into a discussion of how to calculate free energies from first principles. Before I do that, are there any questions about this discussion?
Mike,
Yes.
I have 2 questions.
Yes.
When you plot here the charge density, this is just some iso contour, or is the whole difference, the whole charge is the difference between the atomic superposition and the self-consistent charge?
Yes. So so there is a field, there's a function running throughout the entire volume that you see, and that function is delta rho. Then what I've done is I've taken that function and I've looked at a slice in a horizontal plane, and I've looked at a slice in the vertical plane. Let's look at the horizontal plane. You see this blue region surrounding the body-centered atom?
Okay.
That's a region of charge depletion. And that charge went somewhere. Where did it go? Well, you see that a little bit went into the region of space in between the atoms, but mostly it went up here. And you can see it on this vertical plane.
But what I don't understand is these blobs are just empty ellipsoids, or they are...
These blobs, so in the plane, it shows a cut of this three-dimensional function. Mm-hmm. The blob is an isosurface.
It's an isosurface.
So it's an isosurface of high charge density. and it surrounds even higher charge density.
Okay.
And outside is lower charge density.
Okay, and that one is increasing
Yeah.
because, and that's
And
why you call
yeah,
covalent bonding, basically.
yep. And when I say charge density, I mean density of electrons. Of
Mhm.
course, the electrical charge density is the negative of this, because electrons are negative.
Negative.
But this is the density of electrons.
Okay, this is very interesting. And the second question I have is, once you add electrons to do something like doping, do you just use the pseudo potential without? Do you have in other codes like in VN2K, which we are using, we have to compensate with some positive charge? Do
Yes,
you have to do that in VASP?
that's right. It's done automatically.
Ah, is that automatically? I see.
Yeah.
Okay. And now deviating just a bit from this discussion, if you have, for example, in a material, you do the superposition, let's say some ions with sp carbon, I could say. If you have sp hybridization, if you do the difference, you would also be able, by doing this kind of differences, you'll be able to identify sp1, sp2, or sp3 hybridization, because this will be different than the atomic superposition.
Yes.
Okay, thank you. Yeah.
Okay, so let's start working towards thermodynamics. So in thermodynamics, sort of the controlling function that eventually determines thermodynamic properties is the free energy. For alloy physics, we generally are interested in the Gibbs free energy, which is a function of temperature and pressure. We're interested in that because experiments in the lab are done at constant pressure. And, in a normal laboratory, the value of the pressure is effectively zero on the scale that matters for solid state physics. And so the Gibbs free energy is basically the Helmholtz free energy at the volume that minimizes the Helmholtz free energy. That's because this PV term can be neglected when we're working at laboratory pressures. Okay, so what is the Helmholtz free energy? Well, it's minus kT times the log of the partition function. The partition function Q has a part coming from kinetic energy and then a part coming from the configurations. And the kinetic energy part is kind of trivial and unimportant for everything we're going to be talking about today. But the configurational part is crucial. And here is the expression of the configurational part. So R sub I is the position of the ith ion. So as the atoms move around in space, each R sub I changes, and we have capital N different atoms. And then we have the Boltzmann factor for a configuration. So here we've specified the positions of all the atoms. E is the total energy. And if you take the exponential over kT of the energy over kT, that's the Boltzmann probability that tells us that low energy configurations are favored over high energy. And the partition function is the integral of this. But there's an obvious difficulty in working out this integral from first principles. The difficulty is the time that it takes to calculate the energy for a given configuration of atoms. Depending how many atoms there are, the calculation of the energy might take anywhere from a few seconds up to several hours, or even in very complex cases, it could even take a few days. And that's just to evaluate a single point of the value of the integrand. And then we have to integrate over all space. So we have 3n different spatial integrals to perform, nested integrals to perform. And so that's computationally prohibitive. So we then make a variety of simplifications. that I think of as a separation of terms. And we're going to separate the integral into a sum of terms. So here is my sum of terms. And the sum is over a set of configurations enumerated by the variable gamma. And then so gamma will correspond in the present context. Gamma will relate to a certain arrangement of chemical species. And so every arrangement of different chemical species then accounts for a different value of gamma. Okay. Now, there is an energetically preferred set of positions for a given arrangement of chemical species. What this means is if you put the chemical species on a lattice, there might be small forces due to the random environments. And so we then want to relax those forces. And so every arrangement of chemical species has an optimal relaxed energy. That's what I call E of gamma. And so one contribution to the partition function is a sum over these chemical configurations of the Boltzmann factor for the relaxed configuration. But of course, in these integrals, we have contributions not only from the precise relaxed configurations, but also from small neighborhoods around. And these small neighborhoods around correspond to the atomic vibrations. And so there's going to be a correction to this first term that comes, that I call the vibrational free energy. And for the moment, I'm going to make a further assumption, that is that the vibrational free energy is roughly independent of the particular chemical configuration. That's not precisely true, but it's also pretty close to true, especially when the elements are chemically somewhat similar to each other. And so I'm going to factor that out. Then as a result, the partition function factors into a product of two terms. One of them is the exponential of a configurational free energy. The configurational free energy is the log of this configurational partition function. And the other term is the vibrational free energy that I'll show you how to compute in a moment. And the full free energy then is a sum of a chemical configuration part and a vibrational part. So let me remind you a little bit about how to calculate these quantities. Well, let's first think about the chemical configurations. There will be some exponentially large number of distinct chemical configurations, distinct arrangement of chemical species on the lattice sites. Let's let that number be capital omega. Capital omega is nothing but the combinatorial factor for choosing n alpha atoms of species alpha and placing them among certain sites of a lattice of capital N total sites. And then if we've specified those choices for all of the different species alpha, this is meant to be a sum over alpha of the log of n alpha factorial. Then the log of n factorial minus the sum over alpha of log over n alpha factorial. That is the log of the combinatorial factor, which is the entropy. And applying the Stirling approximation for the factorials, that just simplifies into a sum of minus k Boltzmann times the sum over alpha of x alpha log x alpha. Okay, in the particular case, if we had equal numbers of species, then that would just give us log of n. Okay, Now, so the energy, I already told you the energy we just take is the relaxed energy. And then here we have the entropy, and the configurational free energy is just the configurational energy minus temperature times configurational entropy. But then we also have the vibrational free energy, and the vibrational partition function depends on the chemical configuration. And it is obtained by integrating over the neighborhood of a given configuration the energy for the small displacements away from the equilibrium sites. Okay, so we need to work out this integral. And in the harmonic approximation, you can approximate this energy as a high dimensional paraboloid, the curvatures of which give vibrational frequencies omega. And there is a certain density of frequencies, the vibrational density of states, G of omega. And if you can work out the vibrational density of states and integrate it, weighted by this logarithmic term, that will give you the vibrational free energy. Okay. We will come back to the vibrational free energy, but now I want to make a detour into the connection between the free energies and the phase diagrams. So imagine that we had a function which gave the free energy as a function of composition for each of many different phases. Well, a particular limit of that would be in the limit as temperature goes to 0, where instead of a free energy, we just have energy. But because these are relaxed energies, relaxed at 0 pressure, the technical term for energy is enthalpy, and the symbol for enthalpy is H. So here I show you in the aluminum manganese alloy system, I show you the enthalpies for many different phases. So to make things easiest to see, I'm going to subtract off the enthalpies of pure aluminum and pure manganese in their stable low temperature phases. So here is the enthalpy of aluminum sitting at delta H equals 0, the enthalpy of alpha manganese sitting at delta H equals 0. And then aluminum manganese has many different phases. Some of them are at fixed stoichiometries. Others shown in these ranges of similar colors and labels. Others are higher temperature solid solutions. The predicted phase diagram at 0 Kelvin is the convex hull of the set of enthalpies as a function of composition. So think of the diagram you see here as a scatter plot, with each point in the scatter plot, say this one, corresponding to a certain enthalpy at a certain composition. Some of these points are lower than others, and the frontier of lowest points, which is known as the convex hull, that is the predicted phase diagram. So if we had free energy functions, then instead of having values at isolated points, we would instead have values over continuous ranges of composition, such as you see here. And this collection of continuous functions and isolated points will have a convex hull, and the locus of that convex hull highlights the predicted stable phases. Here we see the convex hull at T equals 0, but we can also look at convex hulls at finite temperature. Okay, so here is the convex hull for indium tin at 0 Kelvin. Here I'm showing the enthalpy. I label it delta G. Of course, at 0 Kelvin, delta G and delta H are the same function. And now I'm showing you enthalpies. I see that there is a question from the audience.
Hello, sir. Actually, due to some network issues, I missed the convex hull part. Can you just briefly say what it was?
Yes. So imagine that you had a function that was free energy as a function of composition at some fixed temperature. Well, each function would have a value at every composition. So for instance, here are these epsilons. They give you the values of the enthalpy in this case as at every composition. And then we also have various isolated points like this point and that point and this one and that one. So we have these continuous functions and isolated points that give values for every value of the concentration. What we want to identify the thermodynamically stable phases is we want to find the phases that minimize these functions. The name for the set of minima is the convex hull. And so the black lines that you see here, that's the convex hull for the set of data that I'm showing. And the vertices of the convex hull, those are stable phases of precise stoichiometry. If a continuous function were to sit on the convex hull, then that would show you an existence range for a solid solution. Here in this case, we only see discrete points on the convex hull, but shortly we're going to see continuous functions on the convex hull as well. Okay, so here is a similar enthalpy diagram for indium tin at 0 Kelvin. And here we see the enthalpy of alpha indium and the enthalpy of beta indium. Indium in the low C over A ratio and indium in the high C over A ratio. Here in black circles, I've added tin to the alpha indium. And unlike the earlier calculation where I varied the valence electron count artificially, here in this case, I actually created a supercell of indium with, I think, 16 atoms. 16 atoms, and I added progressively more tin atoms substituted for the indium. Okay, and then here in red squares, I've done the same for beta. The green diamonds, blue triangles, and the purple star. This is low temperature phase of tin. This epsilon is the high temperature phase of tin, and gamma is the indium tin 4 solid solution. Okay, so what is the convex hull of this set? Well, actually, the convex hull is just the line joining alpha to delta, because every other point lies above that line. So everything you see here in this diagram is above the convex hull, except for the predicted stable phases, alpha indium and delta tin, which of course is in perfect agreement with experiment. But then what is the predicted phase diagram? Well, the predicted phase diagram has two pure phases and nothing in between. So if we started at any composition in between, it would separate into a mixture. Say this composition here would separate into a large amount of indium and a smaller amount of pure tin. But that's the prediction at 0 Kelvin. So now let's go up to finite temperature. So let's go to 173 K. Why such a funny number? Well, it's a funny number because 273 K corresponds to 0 centigrade. And so this is minus 100 C. And here is my free energy function. I have energy minus temperature times entropy. Well, you see how the entropy is varying roughly linearly with respect to composition. That's actually true for all 4 of these phases here. Delta, I'm not even bothering to make any substitution because it's very unfavorable to substitute into delta. Okay, so we have straight lines for E of x. And then we subtract T in units of Kelvin times S of x. And here is the entropy function for assuming random mixing in each of these solid solutions. And so here we see these stable phases. And it's maybe not easy to see, but for instance, this light blue phase labeled alpha, it actually dips below the line that connects 0 alpha to 0 of delta. So that's 173 Kelvin minus 100 centigrade. Here is 0 centigrade. And here you see even more dramatically that the blue and pink have fallen below this line. So certainly some of the blue will lie on the convex hull and some of the pink will lie on the convex hull. And that's even more obvious if we go up to 100 C. So this is now the boiling point of water. So a lot of indium, a large interval of indium will lie on the hull, as will a large interval of beta in indium 310. Okay, so let's look, for example, at understanding the solubility of tin in alpha indium. Okay, so here's our model free energy. We have E0 equals 0. That's the energy of indium without tin. And then if we add a fraction x of tin, it increases linearly. And now we're subtracting T times the entropy. And then to work out the convex hull, we need to carry out a so-called double tangent construction. We need to find a line that is tangent to this light blue curve labeled alpha, which dips slightly below 0. And it also has to be tangent to the point delta that sits at 100% tin and delta G equals 0. Okay, so this is the equation that says the slope at the point of tangency, x, should be equal to the slope of this dashed line. And solving this equation tells us that the solubility limit is approximately e to the minus slope over kt. Okay, so that predicts at 100 K a very small solubility of tin. If we were to do the same thing at a much higher temperature, well, it turns out that things are even more complicated. So here, this is a point of double tangency between the magenta curve labeled beta and the point labeled delta. And then there are 2 points of tangency. This is a point of well, over here, I guess the lines are not sitting exactly where they ought to. But this dashed line should be touching the black curve at a point where its slope is equal to the slope at, oh yeah, here I have an enlargement. Yeah, so this is the point where the slope of the black curve equals the slope of the magenta curve here. And so this dashed line is a line of double tangency. And actually the black and magenta curves lie above the dashed line over this interval. So the convex hull is coincident with the state alpha from 0 up to, in this case, about, it seems to be maybe 9% tin. And then from about 11% tin up to maybe 28%, the convex hull follows the curve labeled beta. But in between, the convex hull lies below the free energy of alpha and the free energy of beta. And so that's a coexistence region. In this region, neither alpha nor beta are stable. Instead, if you started at this composition, you would separate into a mixture of a lot of tin in alpha and a little bit more tin in beta. So you would have a high C over A ratio with 9% tin mixed with a low C over A ratio with about 12% tin. Okay, so that's an example of how to find the convex hull of these free energy functions. Using ideas such as that, this is my sketch by hand. This is a fiction in my own mind and is not the result of precise calculation, although the behavior down here is, and the behavior at this point is also the result of precise calculation. Okay, so this is how I propose to extend the American Society of Metals phase diagram from 0 centigrade down to 0 Kelvin. The composition range, the solubility of indium should vanish to a point in the limit as T goes to absolute 0. The composition range of beta actually pinches off at a finite temperature, not far from 100 Kelvin, a little above 100 Kelvin. And so beta is actually only a high temperature phase. It does not exist in the limit of low temperature. The same is true for gamma, and the same is true for epsilon. And meanwhile, delta, the low temperature phase of tin, again, pinches off to a point. Okay, and that's consistent with what we see here. But there's more to be discussed. One interesting point is that even pure tin exhibits two distinct phases: a low temperature phase that has the diamond structure, and a high temperature phase, which is tetragonal Ti4. It's Ti4, not Ti2 like the indium phases. And it's a slightly more complex crystal structure. So why, as we increase the temperature, do we have a transition from delta to epsilon? Well, notice the energy of epsilon relative to delta is about 24 millielectron volts per atom. That's very close to the value of KT at room temperature. KT at room temperature is about 26 millielectron volts. So it's very believable that there would be a temperature-driven phase transition from this low temperature phase to this high temperature phase. But what is responsible for it? It cannot be random substitution because we're talking about pure tin. So the next thing to think about then is vibrational free energy. And I remind you how to calculate vibrational free energy. So for vibrational free energy, we need to know the vibrational density of states, G of omega. And then we use that vibrational density of states as a weighting factor for the, so here's the vibrational density of states. We use it as a weighting factor for this logarithm, which represents the vibrational free energy for a single mode of frequency omega. Here I have the vibrational density of states. Instead of omega, this is now frequency nu in units of terahertz, so it's omega over 2 pi. I show you in black the calculated vibrational density of states for the diamond structure CF8, face-centered cubic with an 8-atom unit cell. Yeah, that's the structure of diamond. And then in red, we have the Ti4 tetragonal high temperature structure of tin. And you see their vibrational densities of states are quite different. Tin starts off with an excess of low frequency modes. And the diamond structure you see has a surplus of high frequency modes. Those high frequency modes are going to give rise to a high 0 point energy of the diamond structure. And all these lower frequency states of tin, the low frequency states have favorable vibrational free energies. So you can see by inspection that, that the high temperature state has a lower vibrational free energy than the high temperature state. Let's make a graph of those vibrational free energies and see how they compare. So here we see in black the vibrational free energy of CF8, and in red the vibrational free energy of Ti4. At low temperature, the vibrational free energy of Ti4 is high. It's high because we already saw 2 graphs ago that the energy of Ti4 is high compared with the energy of CF8. Okay, so that's why red lies above black at low temperature. But then at high temperature, the vibrational free energy makes the Ti4 state favored. And the two free energies cross at about 375 K. So it's good that they cross. It's a little bit unfortunate exactly what temperature they cross. So it would have made me happier if they crossed at 286K, which is the experimental transition temperature. Yeah, so we overestimated a little bit. And so let's stop and think whether maybe there's a reason for that. Well, a possible reason would be the electronic free energy. So the electronic free energy arises from the smearing of the Fermi surface. So here we have the Fermi occupation function that gives the occupation probability for a single electron state at energy E relative to the chemical potential, which is pretty close to the Fermi energy.
Mike, we see the same slide of vibrational free energy. I don't know if you changed slide.
Okay, yes. Let's see. Okay.
Yeah, no, yes, no.
Yeah.
Sorry.
Yeah, that's the old problem I was having when I started. which I've now learned how to fix. Okay, so here's the Fermi occupation function, and you can use it to weight the electronic density of states in order to calculate the excitation energy and entropy. So the excitation energy just reflects taking states from below the Fermi energy that are occupied and exciting them to levels that are initially unoccupied above the Fermi energy. That gives rise to the electronic energy. Here's the electronic entropy that includes logarithms. And in the limit of low temperature, the electronic free energy is proportional to the electronic density of states times the square of kT. Why is it the square of kT? Well, there's one factor of kT that tells you how far below the Fermi energy you can go to excite an electron. And then another factor of kT tells you how far above the Fermi energy you can put it. Okay, so that's why it goes like kT squared. And we saw that this electronic free energy is proportional to the electronic density of states. So it will favor phases that have a relatively high electronic density of states. So let's look at the electronic density of states. And you see that that tin has a very deep pseudo gap right at the Fermi energy. So almost no electronic states at the Fermi energy, whereas the high temperature phase has roughly a half a state per EV per atom. So if we work out the value of the electronic free energy, it turns out to be about a half of a milli-electron volt per atom. I left off the minus sign. It's minus 0.0005 EV. We needed about minus 0.005 in order to get the correct transition temperature. So we're not quite there, and I'm in the middle of trying to figure out what exactly is missing. Maybe spin orbit coupling might be needed in order to get things quantitatively more accurate. So so that's on the to-do list. Are there questions at this point about indium tin before I turn to the high entropy alloy? Okay, so now let's switch gears a little bit. So high entropy alloys are a very hot topic, especially in material science these days, where it's thought to be a new design principle for the design of potentially useful new materials. What is a high entropy alloy? Well, it's just like a solid solution that we've been discussing before, except that it has even more chemical configurational entropy. And you get more configurational entropy by having more distinct chemical species. So here in this case, we have a 4-element refractory alloy, MONBTAW. And at high temperatures, it makes a random distribution of atoms among sites. And so the entropy would be about log 4. Log 4 is log of 2 squared, which is twice log 2. So this has twice as much configurational entropy as a binary alloy. And so it then can be used to stabilize a single phase at high temperature. But at low temperature, there are certain patterns of preferential chemical interaction among the different species that will lead to chemical ordering. And the color coding here is such that the cool colors, which are dark blue and light blue, They alternate with the warm colors, purple and red. Okay, so the purple and red alternate with the shades of blue, purple, red, blue, purple, red, blue, purple, red, blue, and so on. And so this is a kind of a cesium chloride type of chemical order on a body-centered cubic lattice. But it's a funny one because the cube vertex sites are preferentially occupied by molybdenum and tungsten, while the body center sites are preferentially occupied by niobium and tantalum. But within each sublattice, there is random disorder. So you have random substitution of niobium and tantalum, but within their preferred sites. And then at even lower temperatures, we get a phase separation into a mixture of molybdenum and tantalum, showing this perfect chemical order: molybdenum, tantalum, molybdenum, tantalum, molybdenum, tantalum, coexisting with a different kind of structure. It's called the B32 structure of niobium and tungsten. Okay, so that's the behavior of this alloy. And we can simulate this using Monte Carlo simulations. And then we can maybe I was pointing to the wrong thing when I was showing the chemical order. I have two screens here that confuse me. So this is purple pink alternating with shades of blue. And then here we have purple dark blue alternating and light blue pink forming this other structure. Okay. Now we can carry out Monte Carlo simulations of this material. And it's a refractory alloy, so we can go up to very high temperatures. And what we see here, what I'm showing you here is the prevalence of near neighbor bonds. So Y alpha beta is the frequency of bonds between chemical species alpha and chemical species beta. X alpha and X beta, those are the concentrations of alpha and beta. Alpha and beta run over MO, NB, TA, and W. So X alpha and X beta are both a quarter. In the absence of any chemical order, Y alpha beta would be 1/16. That's the square of 1/4. And so this ratio would equal 1 in the absence of chemical order. But what I've drawn for you here are the relative frequency of near neighbor bonds. Here is a little fragment of a body-centered cubic structure, and these yellow bonds along the diagonals, those are the near neighbors. And you see that actually, even at high temperature, there's a slight preference for molybdenum tantalum near neighbor bonds. And at the same time, there's a deficit of tantalum and molybdenum bonds at near neighbors. The preference is weak at high temperatures, but then we pass through some sort of a transition at around 700 or 800 Kelvin, at which point there's a sudden jump in the preference or dispreference. And exactly the opposite happens if you look at next neighbors. Next neighbors are the blue bonds. So why does that happen? Well, we can calculate relative interaction strengths of these different species by looking at the behavior of binary alloys. And what we discover is that the strongest interaction is between molybdenum and tantalum. with a strong preference to be near neighbors. And then the next strongest preferences are between elements on adjacent columns of the periodic table. So here in the periodic table, this diagonal is the strongest interaction. These horizontal ones are next strongest. The diagonal is also pretty strong. And then the vertical interactions within the columns are quite weak. That's the reason that we see these patterns. So the strongest interaction is between MO and TA. That's why MO and TA likes to separate and form a pure phase with strict chemical order. But then we're left over with NB and W, which themselves do have a certain chemical ordering preference. But at high temperature or intermediate temperature, we do have random substitution of pinks and purples. Okay, so the pinks and purples are not strictly ordered at intermediate temperatures. Okay, and we can understand that behavior as the result of contrast in atomic volume and in particular in electronegativity. Okay, and one thing that we can do with these correlation functions that we calculate from Monte Carlo simulation, we can calculate the entropy using a method that I call cluster variation method. So the cluster variation method is a way of writing down the entropy if we know certain things about the distribution of chemical species among the sites. So for instance, if we knew how many ways there were to arrange atoms among the M sites of a crystal lattice, given that we have mole fractions X alpha, that entropy, which I call the independent point entropy, is just minus the sum over species of X alpha log X alpha. That's also known as the Bragg-Williams entropy. But we can also include correlations. And so the inclusion of correlations gives us, the correlations that I'm going to include in particular are nearest neighbor pairs. And if the nearest neighbor pair frequencies differ from the product of the single site occupations, then we can calculate a quantity known as the mutual information, which is the information content of this correlation function. And according to principles of information theory, the entropy can be expressed as the entropy of ideal mixing minus the number of bonds per site times the information content of the correlations along these bonds. So within information theory, we think of this as removing the redundancy. We remove redundancy in the amount of information required to specify the chemical distribution. And then this can be generalized to include 3-point and 4-point correlation functions. And the generalization is known as Kikuchi's cluster variation method. And then we can use this to calculate configurational entropy of the high entropy alloy. So in the limit of high temperature, the entropy should approach random mixing, which is log 4. But if we then include the entropy reduction due to nearest neighbors, we see that even at high temperature, there is a small loss of entropy due to the weak correlations that we had observed in our calculations. but the entropy loss accelerates at low temperature. Yeah, so here we are looking at near neighbors, which are these yellow bonds. But we can also include next neighbors, which are the blue bonds, or triangles. So a pair of yellow and one blue bond make a triangle. And we can even compute the 4-point correlation function associated with this tetrahedron. And here is a formula written down in cluster variation method notation to give us the entropy at the tetrahedron level. And these are the entropies that would be predicted according to the different methods. You see that, yeah, the entropy reduction due to near neighbors is pretty well captured. The exact entropy is pretty well captured even at the near neighbor level until we pass below that phase transition, at which point we need to use the full tetrahedron entropy to get an accurate result. Okay, so I just want to summarize now. What I've been doing is I've been taking the density functional theory total energies, which are calculated from quantum mechanical first principles, and then I have treated the DFT total energy as if it were a Hamiltonian in classical mechanics in order to apply classical statistical mechanics in order to calculate the configurational free energy. So I combine two different first principles. One of them is DFT, the other is statistical mechanics. And I use that to create model free energies, including the entropy. And then with these model free energies, I can do various useful things, like I can predict the low temperature extension of the phase diagram of the indium tin alloy. And I can look at configurational entropies of high entropy alloys, and I can do many other things as well. Okay, and with that, I think we have maybe 5 minutes left for questions.